Parametric Equations Part 4, Vector Calculus. Let x of t, comma y of t, notice the brackets. That is one of the notations we use for vectors. Give the parameterized position p of an object at time t. Then the velocity vector v of t is simply the vector x prime, comma y prime. Just take the derivative of each p separately. And the acceleration vector a of t is x double prime, comma y double prime. Do two quick examples here. Suppose we have the position vector given by cosine of t squared, the natural log of 1 plus 2t. And we'll say this is for t greater than or equal to 0. What is the velocity vector at t equals 1? Well, the velocity vector at t is x prime, so negative, I'm going to leave a little space, negative sine of t squared times the chain out 2t, comma, y prime, the derivative of natural log is u prime over u, and then v at 1 is negative 2 times the sine of 1, comma, 2 over 3. And there's my velocity vector at t equals 1. Let's also find the acceleration vector just at t. So the acceleration vector is x double prime, or v prime, I'll call it vx prime of t, comma, the derivative of the velocity in the y direction of t. So let's take the derivative of the x part of velocity. All right, we have a product rule heading our way, so negative 2 times the sine of t squared plus negative 2t times another 2t cosine of t squared. Now let's take the derivative of the y part. I'm going to rewrite it over here to make it simpler. This is 2 times 1 plus 2t to the negative 1. So I would get negative 2. I'll do the derivative right here. Negative 2, 1 plus 2t to the negative 2 times a chain out. So I get negative 4 over 1 plus 2t quantity squared. There's my acceleration vector. Second example. Let our acceleration vector be given by t cubed over 3, comma, negative sine pi t, and suppose that we know that the velocity at 1 is given by negative 1, comma, negative 2 over pi. Let's evaluate the velocity, or the velocity vector at t equals 2. Well, if acceleration is the derivative of velocity, then velocity is the integral of acceleration, of course. So we can do these in pieces, because I can do the x part and the y parts separately. So the velocity of the x part at t equals 2 is our starting velocity, if you would, -1, plus the integral from 1 to 2 of the acceleration in the x direction. So if I continue on, I get -1 plus, and then I have t to the 4th over 12 from 1 to 2, which will give me -1 plus, and I'll plug in my top limit, 16 over 12, minus plug in my bottom limit, 1 over 12, which equals -12 over 12 plus 15 over 12, which is 3 over 12, or 1/4. How about the velocity in the y direction? The velocity in the y at 2 is my starting value, the velocity, the acceleration. No, I spoke correct the first time. The velocity at 1, -2 over pi, plus the integral from 1 to 2 of the acceleration in the y direction, which is -2 over pi, and then the antiderivative of negative sign is positive cosine. I'll leave a little space. So cosine of pi t. But it's technically a u sub, so I would need an extra 1 over pi right there. From 1 to 2. This gives me -2 over pi plus 1 over pi times the cosine of 2 pi, 1, minus the cosine of 1 pi, -1, which is -2 pi plus 2 pi, which equals 0. So the velocity vector at 2 is 1/4, 0.